Okay, in this video I'm going to teach you about position, velocity, and acceleration of a particle or things moving along a line. So projectiles, linear projectiles. There's some theory involved here, and so let's tackle that first. The first of which is, we call it a height function, or sometimes I've seen it as an S or even an X of t, and that just describes a position of a particle or position of a rock being thrown along a line, or at least for our case it will be for now along a line. If we take the derivative of that with respect to time, and we'll differentiate the height function with respect to time, we get the change of height with respect to the change in time, and that has meaning. We call that the velocity. And velocity is not only speed, but it's a directional speed. Positive velocity means it's moving upwards or to the right. Negative velocity means we're moving downwards or to the left, depending on the context. So speed and velocity are similar, but speed really is, for the record, the absolute value of the velocity. Okay? But as far as the calculus is concerned, velocity has a sign which is meaningful, and the derivative of the height or position function is what we call velocity. If we differentiate now that velocity function with respect to time, we get the change of velocity with respect to time, which we happen to call the acceleration. Okay, and so what we get is, as we kind of differentiate through this chain, we get each particular idea or notion. Okay, the change of position with respect to time, the derivative of the position, height, is a velocity, and the derivative of velocity, the change of velocity with respect to time, is called the acceleration. Okay, so that said, let's look at a particular example, and for now we're going to stick with what I believe was developed by Newton, and that is this general height function for something thrown upwards or downwards or dropped. Okay, so again, we're looking at motion along a line of a projectile, not thrown at an angle yet, simply hurled upward and downward or dropped. So we have this general quadratic that describes that particular height or position of that projectile or particle, and it's half of g, and g is the acceleration due to gravity, which in feet is 32 feet per second squared, or in meters it's 9.8 meters per second squared. So depending on if we're thinking about height in feet or meters, we use the appropriate gravitational pull. The acceleration due to gravity, we call that. Plus the initial velocity times time, that's the initial velocity. If we're simply dropping something, there's no initial velocity. If we're throwing it upwards, there's a positive initial velocity. If we're throwing it downwards, a negative initial velocity. Plus the initial height, and we call that h sub naught or h sub o, and that is the initial height from which we're dropping a rock or whatever the case may be. So that was established by Newton, I believe, long ago, and we're going to use that. So let's take a look at a particular example. And for this example, let's say we're on top of a building. There's Allen Building. We're on top of the clock tower, and let's just assume that that's 100 feet. And in sheer joy, we're going to throw our calculus book upward in the air. Straight up, and it's going to come straight down. Okay, and so let's assume that that particular throwing has an initial velocity of 30 feet per second. So we're talking feet. So therefore, the position or the height of this calculus book being hurled upwards into the air will be modeled by this particular function, negative 16t squared plus the initial velocity, which I believe I said was 30 times time, plus the initial height, which is 100 feet. And we're dealing in feet here. Height is in feet. Okay, so that's the appropriate function that models the height of this book at any moment. And so we can answer a lot of questions regarding this particular book travels. And here are some of those particular questions that we could consider. First of all, note that that is a parabola, the height function. And this is not the path, but the height. Starts over here at 0, 100, opens downwards, and looks kind of like that. Again, that's not the path of the book, but that is a function that at any time t describes the height. Okay, so one particular question that might be interesting is, hey, what's the maximum height, and when does that maximum height occur? So recall that to find a maximum value, actually I'll write that question. So what is the max height that this book will achieve, and when? And recall to find the max for a lot of the functions we've been dealing with, you find the derivative set equal to 0 and work from there. So we're going to do the same thing. The derivative of the height function gives us, recall, the velocity. The change of the height with respect to time is the velocity. And the derivative of negative 16t squared is going to be negative 32t. The derivative of 30t with respect to t is 30, and the derivative of the 100 is 0. So that's a function that describes the velocity, and we want to know when the velocity is 0. That will be at this moment in time, that blue spot on the t-axis. That's a height axis in feet. So we want to set that equal to 0. Bada bing, bada boom. And lo and behold, when we solve for t, we get negative 30 over negative 32, which simplifies to 15 over 16. So at almost 1 second, we have a 0 velocity. And if you imagine this book being hurled upwards, since it's going upwards, we have a positive velocity, noted by the positive slope on the position function, the height. Then it instantly stops. Stop. At which time it changes to dropping. And we have correspondingly on the height position function, we have negative slope. So you have positive, 0, negative as far as the derivative, the velocity of this, positive, 0, negative, and therefore that makes that a max. So to get the actual maximum height, I'm going to plug that almost 1 second, 15/16 into the height function, and I'll leave that for you guys to work through. Okay, and that gives us the maximum height value, okay, which occurs at a little bit less than 1 second. Okay, so the travel of this book based on the velocity and height function, the velocity will be positive all the way up until 15/16 seconds, and then be negative after 15/16 seconds. So the book's going to go up for almost 1 second, stop at 15/16 of a second, and then drop. Okay. Another idea we can consider is when this, or we can at the very least consider acceleration. So what's the acceleration look like of this? And again, the acceleration is a change of the velocity. And so let's say, what's the acceleration of this book a little bit after it hits its maximum height, a little bit after 15/16 seconds at 1 second. And so to find the acceleration, I'm going to take the derivative with respect to time of the velocity. And recall, here's the velocity function, which is the derivative of the height or position function. So I'm going to differentiate this once more to get the acceleration function. And so I differentiate negative 32t to get negative 32 plus 0, which is the derivative plus 30. And oh, lo and behold, that's my acceleration, which should be a constant on planet Earth. That's due to gravity. And that's measured in feet per second squared. And that's a constant. Our Earth is pulling things downward due to gravity at a rate of negative 32 feet per second squared. And so at any moment in time, this book, which is being magically hurled up into the air, is being pulled down by gravity at the rate of negative 32 feet per second squared. Okay? Thanks for listening. To summarize, we have the theory. The derivative of a position function is going to be the velocity. That's a change of height with respect to time. We call that velocity. And the derivative of the velocity function, change of velocity with respect to time, is called the acceleration. So if as we work down this chain, we differentiate, we get another meaningful idea, which is related to the original position or height function. And for these particular examples, we're going to stick for now with Newton's motion along a line. I think these are called projectiles. This is the general formula. V sub naught is your initial velocity. H sub naught is your initial height from which you're throwing or dropping. And g is your acceleration due to gravity, which either in feet is 32 feet per second squared or meters 9.8. Okay, and here's an example that we worked out using those ideas. So based on a particular word problem, we can find the height, the velocity, acceleration of a particular object being thrown upwards, downwards, or dropped. Thanks for listening. Bye-bye.